So guys, we are going to start our discussion on assembler directives. Okay. So here what is the first thing that you have to understand is instruction. We know instructions are what? Instructions are the commands which is given to the CPU. Okay. There are two types in which you can give this command. That is assembly language, which is a human readable form, and machine language, that is a binary form of zeros and one. So here assembly language is like add s1 comma s2 comma s3. This is an assembly language. Now CPU can understand only the binary form. So what is assembly? So disk 5, you have to understand that there are basically two types of languages. Okay, so instruction is what the commands that you're giving to the CPU. Now the next thing that you have to understand, there are two kind of languages. Assembly language is the machine language is the. Now when I'm talking about assembly language is a human readable format. Okay, and machine language is a computer readable format, which is in the form of zeros and one. Okay, now you have to understand that if you're saying, but when you want to discuss about assembly language is nothing but the human readable for representation of a machine language instruction. So when you have a machine language, that machine language instructions, human readable form of that machine language instruction, if I'm taking, that is going to be equal to what? The assembly language. Okay, so how can we convert the machine language into the assembly language? That is using the assembling method. Okay, so here if you see, assembly language is a human readable language, okay, which is the representation, human readable representation of a machine language is the assembly language. Fine, like that also you can say. Then you have to understand the concept of mnemonic and operands. Now if you consider an instruction, let us see, add LW, add LW, SW. These are what? These are the operations, right? These are some operations. Okay. So these operations are basically known as what? The mnemonic. These operations are basically known as what? Mnemonic. Now, operands are what? Like if I'm writing add S1 S2 comma S3 means add would be what? The mnemonic, the operation we are doing, and S1 S2 S3 are what? The operands. These are what? The operands. Okay, so now I hope you have understood what do we mean by operands and what do we mean by mnemonic. Mnemonic is what? Mnemonic is the operations.
You are going live code?
Okay, mnemonic is the operands, and mnemonic is the operation, and operands are the data in which these operation is being happened. And when the question is like what is assembly language, then you will say that assembly language is a human readable representation of a machine language. Understood that? You will say. Then this is just an example. Here you have a high level code. You are going to convert that high level code into RISC-V assembly code. This we know. How you will add B and C. Okay, you're going to write it like this. You're adding B and C and storing that result in A, right? This is the RISC-V assembly code of it. So there are B and C are called as the source operands. Here you have to understand that the B and C is known as the source operands because these are the source where you're adding them. Now A is what? A is the destination operand. A is what? A is the destination operand. Now this is another example for sub instruction is given here.
It's only 24 MB.
Now you have to understand
No, it's only 24 MB.
that
Not that much.
there are some design principles. Okay, the first design principle, as you can
No,
see,
it's
is
not
this.
so bad.
While you are designing the first design, that while you're designing an assembly language, okay, that is what we're talking about. When you're designing an assembly language, the first principle is simplicity favors regularity. Means keep always the instructions simple and uniform. You can say that in a very simple way. Simplicity favors regularity means the first thing that you can say is that you have to keep the instructions simple and uniform. You are keeping the instructions simple and uniform. This is the first design principle. That means always all the instructions should have a same instruction format. That means all the instructions should look familiar, and it should be easy to easy for hardware. So all the instructions should look familiar here, and same number of operands, that is 2 source and 1 register, sorry, 1 destination, and easy hardware design, because instructions are simple, fast execution and less complexity is needed. So what we are talking about here is that, what we are going to talk about is that simplicity favors regularity, means the instruction should always be simple and it should be uniform. That is, the number of operands should be same, the instruction format should be same, you should have a consistent easier format, and it should be easier to encode and handle in hardware format. Okay, when you're talking about hardware also, same instruction format means all instruction should be easy to understand as well as easy for hardware. Same number of operands means 2 sources and 1 destination register, that should be maintained. Then it should be easier to encode and hardware should be easy to handle. This is the first design principle. Understood? The design principle first is to keep the instructions simple and uniform. So here if you see, you have A is equal to B plus C minus D. It is a single line. So the assembly program stores the intermediate result. So B plus C is stored in a temporary register, that is T, and that value added with, that value is subtracted with D. So B plus C, that value is subtracted with D to get the final result and store it in the A. So if you have multiple assembly language instruction to perform more complex instruction is an example of second design principle. That means second design principle says that smaller is faster, means you have to use only few simple instructions.
Did you update
So
your VM?
the first design, that is a second design principle, is that use few simple instruction instead of one complex instruction. Write few simple instructions. That is what the second design principle says. That means here, if you have one simple instruction, this 5 would avoid complex instruction. That means simple instructions are much more faster and efficient. Okay, so when you have the instruction that you have shown here in the before, you are divided that into 2 instructions. So that means the RISC-V always would make sure that if you have a complex instructions, that is performed using multiple simple instruction. Like if you have, this is a complex instruction, so that complex instruction you are breaking down into multiple simple instructions, which is easy to basically do. So we are using simple few instruction, that is design principle number 2. So design principle number 1 of assembly language is that first you have to keep it simple and consistent. The instruction format should be always be consistent. Instruction format consistency means what? The instruction looks similar. They should be easy to understand, easy for hardware, and they should use the same number of operands, and it should be easier for encoding as well as for handling the hardware. This is what first design principle means. Keep the instructions simple and uniform. The next instruction means that you have, if you have a very complex instruction, that you want to basically convert into few simple instruction. In like in here, CISC is a complex instruction set, but RISC is a reduced instruction set. So only small number of small instruction is supported in RISC. Okay, in the next video we will discuss very clearly about the difference between RISC and CISC. So stay tuned for that. Now here we have discussing the design principles, right, of the assembly language. So design principle number 2 is over. Now if we look here, the next thing you have to understand is that operands. That is, if you see an instruction operates, we know if we got an instruction, that instruction is operating on operands. The variables A, B, C are all operands, but the computer is operating on 1 and 0 and not variables. The instruction at a physical location from which you can retrieve that binary data. So operand location is basically what? Physical location in the computer. That can be registers, memory, or constants, that is immediate value. So you have to understand that the operands are what? Operands are the in which the variables in which you want to act, but they are binary form. So what happened is that the registers are there, which registers are there in memory. Also you can get the data, and constants are there, which is the immediate values, that we know how the immediate value works. So registers means what? Registers are fast but they are limited. This size is less. But memories are slow but they are very large. So they are used for storage purpose and all. But registers can be used for computation. Like while you're doing some particular calculation, particular operation, what are the data operands that is required that time, that will be stored in the register. So registers can be used for computation purpose. CPU can works only on the registers. So if you want something from the register, you have to take that from the memory, put it in the register, then the CPU can do the operation. So one important thing that you have to understand, the CPU would only compute the things which is present in the register. So if you want any data, first you have to take it from the memory and put it in the register, then only the CPU can access that. Understood? So this is one important thing that you have to understand. So that is what registers instructions, that is operands, registers, we know. In RISC-V there are basically 32 registers which is called as register state, stored in a small multi-port memory that is called as the register file. So the operands that the CPU, I told you CPU can access only registers. So these operands are present in the register. So if there is nothing in the register, it has to take the data from the memory and put it in the register, then only the ALU can compute it. Okay, that is what we have said earlier. CPU works only with the register. The RISC-V register, there are 32 registers. These are called as the register set. Now these registers are stored in a small multi-port memory, right? These registers, where they are stored, these registers stored in a small multi-port memory that is called as register file. Fewer the register, the faster they can be accessed. This led to a third design principle. So here if you understand, the number of register is less, then that much faster it can basically get accessed. So fewer the register, faster is how you can access that. So that would give us the third design principle that you have to understand. So third design principle means fewer the register, faster is the access, is the third design principle you have to understand. Now register, I told you 32 registers are there. They are called as the register set and they are stored in a small multi-port memory that is known as the register file. Okay, so the operands are the registers, memory constants. We know they can only, computer can operate only ones and zero and not on variables. The instruction needs a physical location from which you have to retrieve that binary data. So that instruction needs from where you're going to retrieve the binary data, you can retrieve from register, memory, constants. Three things are there, three operands basically are there. Now while you're taking it from the registers means what? Registers store the data very fastly, right? But it is slow, but it is used for mainly for computation purpose because CPU can access only the register. Okay, so RISC-V has how many registers? RISC-V has 32 registers, which is called as a register set. Now it is stored in a small multi-port memory that is called as a register file. So fewer the number of registers, the faster it can access is a third design principle. So we discussed so far three design principles. The first design principle is simplicity favors. Simplicity is more favors regularity. That means you have to make the design much more consistent and also simple. That is the first design. Keep the instructions simple and uniform, that is consistency. So means the instruction format should be consistent, the encoding, the handling of the hardware and all should be easy, the number of operands that uses should be same. The second design principle was that complex instruction has to be divided into smaller instructions. And the third design principle, I told you, number of registers increase, the lesser the number of registers, the more speedily, the faster you can access it. So you have to have fewer registers, okay, then only you can fastly access it. Then constants and immediate, we know. In addition to this register operation, RISC-V instruction can also use constants or immediate operands. These constants are called as immediate because the value are immediately available from the instruction. I know. Add I S0 S1 comma 1. So that means I am adding S1 with 1 and putting the value in the S0. So that means immediately in the instruction itself. Add I means immediate instruction we are adding. So the immediate value is already given in the instruction itself, directly given. So you don't need to access it from the register or from the memory and all. You don't require a register or a memory access to get that data. You don't need here because you get it directly from the from the instruction itself provided directly to us. So we don't need to
Pink.
Need a separate way in which for storing this part.
I want to retrieve.
Fine. Now you have to learn this RISC-V register set. Okay. So how we are going to learn is
I
that
see
first
yellow.
of all x0 we know up to x0 to x31 there are general purpose registers available to us. Now x0 would always have the constant value 0 to us. Now what does x1 to x31 have? That is what you have to understand now. x1 contains what? The return address. x2 contains a stack pointer. x3 contains a global pointer. x4 contains a thread pointer. Now temporary is temporary, you have to understand that first x5 to x7, that is the first temporary registers are coming. x8 is a saved register or a frame pointer. Again x9 is a saved register. Then function arguments or return values from x10 to x11, that is the A
The pink.
function
is
arguments.
very good.
Then x12 to x17 contains again function arguments. Then you have again saved register from s18 to s26. Then finally s28 to x31 you have another register. So how are you going to learn? So actually you have to learn this RISC-V register set. So this is also something that you have to understand here. That is why it's given table here and you have to learn that. Fine. So we told that how many register sets are there? x0 to x31. x0 I told you, this we can easily learn. x0 constant value, x1 stack return address, x2 stack pointer, x3 global pointer, x4 thread pointer. This is this much till s4. I hope it will be clear.
I think
s0, s1, s2, s3, s4. s0 is what? The constant value 0. x1 is the return address, x2 is the stack pointer, then global pointer and thread pointer. Right, up to this much it will be easy to learn, right?
Yes.
If that is, then you have to up to this much first if you try to learn. This is x0 is 0, return address RS, stack pointer SP, global pointer GP, thread pointer TP. That is done. Then you are coming temporary register. Then T0 to T2. There are three temporary register that is coming from S5, S6, X7. So the next try to learn this part. Okay, my main idea is to teach from the video itself. That's why I'm taking this much time. Okay, so here if you see constant value 0, we have taken return address, then we have the stack pointer, global pointer, thread pointer. Then I told you T0 to T2 there are some temporary registers there, so it will be S5 to X7 there are some temporary registers. Then you have one saved register or a frame pointer. You have a one saved register or frame pointer, that is S0 or FP, that is frame pointer. Fine. Then you have one saved register S1. After that you have one saved register S1. So till now what we learned, we have a constant value x0, then return address, stack pointer, global pointer, thread pointer. Then we said that T0 to T2 8 temporary registers are there. Then I told you that there is a saved register or frame pointer. That part is the S0 or FP. That is the first saved register which we have talked. Then after that I told you that there is one more saved register, that is S1. So till X9 we have reached. Okay, so if I'm taking a blank page, first where we have started with x0. Okay, this is the 0. Fine. This we have done. Then we have x1. This is what a return address. Then we have x2. x2 that is, then s3 is the global pointer, then x4 is the thread pointer. Fine, this much we have already read. Then I told you temporary registers is coming. T0 to T2 temporary registers are coming, which contains 3. So x5 to s7 temporary registers come. Then one saved register or frame pointer came here, that is S8. Then another saved register S1 come, which is X9. Okay, this we have understood. So we have learned that, right? Saved register, this we have learned. Fine, this much we have learned till x9. Now we have function arguments, that is this function arguments or return values. Function arguments or return values a0 to a1. Then a2 to 7 rest of the function arguments. A2 to a7 contains the rest of the function arguments. Finally, the rest of the saved registers and temporary registers will come. Saved register is from S2 to S11 because S0, S1 is already covered. So S2 to S11. Then temporary registers we have covered T0 to T2. So we have left with T3 to T6. Rest of the temporary registers. So function arguments or return value, first A0 to A1. Some two function arguments or return, one for function argument or return values, that is a0 to a1. Then a2 to a7 you have the rest of the function arguments. Then saved register, rest of the saved register from S2 to S11 because S0 S1 we have covered, so S2 to S11. The rest of the temporary register T3 to T6. So if I am talking this starting again we have S0. Okay, we have S0, that is the 0, and then you have the S1, that is the return address. Then you have the S2, that is the stack pointer. X3, that is the global pointer. X4, that is a thread pointer. This much we have discussed. Now next we have, after that thread pointer, I told you that is temporary registers T0 to T2. Some temporary registers would come. That would be what? We have till now S4. So S5 to S7, right? Then I told that a save pointer, that is S0, a saved pointer, a frame pointer is coming, that is X8. Then another S1 contains another saved register key. Okay, fine. Now an argument, function argument or a return value is coming here. So a function argument, a return value is coming here, that is a0 to a1. Then rest of the function argument is what? a2 to a7. Rest of the function arguments come. Then I told you rest of the saved registers would come. So S0 S1 is a save register. Now we have S2 to S11. And rest of the temporary registers we have done T0 to T2. Rest of the temporary registers T3 to T6. Okay, so rest of the temporary registers come. So that means here A2 to A7, if I am taking A2 to A7, just count how many registers would be there, right? A0 to A1 extend to X11, then X12 to X17 would come. Then we told that saved register is coming from S2 to S11, so that means S18 to S27. Like that you just calculate it. Fine. This much, this is how you can learn the RISC-V register set. Fine. So I told you that x0 always holds what? The constant value. Okay. So here if in this code you have, and the save register S0 to S11 and T0 to T6 are the temporary registers and 0 holds. So these are the some things that you have to note here. Okay, now if you see this, add B plus C. So B and C are some saved registers, so I have added that value here. Now this is immediate values case of, this is an immediate value RISC-V assembly code. Now here you see I am adding A plus 4. Okay, and again add immediate value minus 12. Like this, how we are going to deal with immediate operands. Immediate operands come, you are going to write it like this. Fine. This much we have understood. So we have also discussed 3 design principles. Simplicity favors regularity. It should be constant. Instruction format should be constant. That is what the first thing in here. The number of operands should be same. Encoding easier, encoding and handling of the hardware. And the second design principle, if you have a complex instruction, you're going to divide into simpler instruction. The third is that if the number of the registers has become fewer, the number of registers faster would be the access. This is the 3 design principle we have discussed here. Now the next question is that you have to transfer this high level code to an assembly language code. So here what happened, B and C I am going to subtract. I am going to put that result into A, so that A is stored in a saved register, B is also saved register, C is also saved register. So I am subtracting B and C, and that value I am putting it here. Now here G plus H are in a saved registers. Their value I am adding and putting in a temporary register T0. Similarly, I and j I am adding and putting it in a temporary register T1, and T0, T1, these temporary registers I am subtracting to put it in a new saved register, that is S3, that is F. Fine, F is S3 is given here. So try to do this. When I am creating any temporary things in between them, we will create temporary registers. That itself, that is only thing here. Now here if you see operands, that is memory, too much data to fit is fit in only two less data will be fitting in that 32 register. So if you want to store more data, we will put it in the memory, but memory is large but it is slow. Commonly used variables is kept in the register. In RISC-V architecture, instructions operate exclusively on the register. So CPU can only CPU is basically computation basically is happening through the registers only. So what happens is that data is stored in the memory, has to be moved onto the register, then only it can be processed. RISC-V uses byte addressable memory, that I told you. Byte addressable memory is what RISC-V. Each byte has a unique address in the memory. This we have already discussed that in the previous videos itself. We have discussed that it is byte addressable, that is each of the byte would have an address in the RISC-V. Fine. Now let us discuss about assembler directives. Now we are going to come on about our discussion on assembler directives. What do we mean by definition? What is the definition of assembler directives? Assembler directives are the commands which is given to the assembler to organize memory and data not executed by the CPU. That means they are the commands which is given to the assembler to organize the memory and data, and it is not executed by the CPU. They are just the commands that is given to the assembler. Assembler directives are nothing but the commands that is given to the assembler, and it is not executed by the CPU. That is one important thing that you have to understand. Not executed by CPU. Okay, they are just the commands. They are the commands which is given to the assembler. So they are the commands which is given to the assembler, but they are not executed by the CPU. This is one you have to understand. Okay, so in order to organize, why it is done? To organize the memory. Okay, it basically to help allocate memory, to define the variables, do not generate machine code, also called as pseudo ops. So here it means that here you have to understand what is assembler directives, why we are using the assembler directives, and also I will teach you that. First, whenever assembler directives question come, first we have to say the one thing is about the what is assembler directives. Then what are the key points that you can say in assembler directives? So assembler directive, I told you, assembler directives, first you are going to say it like this, are commands which is given to commands wait a minute, okay. Okay, they are the commands given to assembler. So they are the commands which you are giving to the assembler. Why? To organize the memory, to organize. So they are the commands which is given to the assembler to organize memory and also data, to organize memory and data. And one important thing is that they are not executed by the CPU. Just like their commands, they are not like in the processor and it will go to different stage. No, they are not executed by CPU. Okay, this much we have understood. This is the definition. The key points is that they help allocate the memory, they help to define the variables, and they do not generate any machine code, and they are also called as pseudo ops. So the next important things that I want to, some key features you can say while you are talking about assembler is that they help to allocate memory, they helped to allocate memory, first point. Second point is that they help to define variables. They help to define variables. The third point is that, right, help to allocate memory. They help to define the variables. The third point is that they are called as pseudo ops. They are called as pseudo ops, right? And they do not generate machine code. Do not generate machine code. So these are the things, important things that I want you to remember about this assembly directives. So first I wanted to to remember what is assembly directives. They are the commands which is given to the assembler in order to organize the memory and data, and it is not executed by the CPU. And the next thing is the key features of this assembly directive. They are helping to organize the memory. They are also known as pseudo ops. They help to define the variables, and they do not generate the machine code. So there are some important directives. That is what we are going to discuss about these important directives. The first is the .test directive. As you can see, the first important directive is this .test. Now what does .test do? They store the program's instruction. .test contains the instruction which is currently executing, stores that program's instruction. Okay, .data is what it do. It stores this initialized variables. Okay, storing the initialized variables are done by the .data. Now .bss means what? Store the uninitialized variables. And .raw data means what? It is used to store the constants, that is the read only data. So here these are some of the important directives, common directives which is used, is this .data, .text, .global. So first let us understand this four first. First let us understand this four important directives. So for that, I need a page. Okay, here there is a page. I'm using that page. So first let us understand. First I told you that we have .test. .text means whenever we are starting to write our program instruction, inside this .test we will write the program instruction. So we'll write first the .text, then we will write the instruction, whatever is the program instruction we will write there. And .data, I told you, they will contain the initialized variables and all are stored in .data. That means in .data, first I will say that, okay, A is there, and here word is 10. That means A has this word 10. Okay, .data. Now .bss means what? Is storing uninitialized global variables. Now raw data. Raw data, as I told you, they are basically used to store what? Constants. Used to store constants. That means read only data. Raw data, it's like read only, RO, read only data, or used to store the constants. .bss is uninitialized global variables. .data is initialized global variables. A, then you have double colon you have, then word 10. This is how one example only we are talking about here. So I wanted you to discuss some more examples of this assembler directives. So I want to that important directives we have to discuss here. So this table, if you check, .text contains the text section, .data contains the global data section, .bss means what? The uninitialized data section, and .section .foo means section named .foo, right? .section means we are creating a section and the name of the section is like .foo. Align in means what? I am aligning the next data or instruction on 2 raised to n byte boundary, and balign n means I am aligning the next instruction or data on a n byte boundary. Okay, and global sim means labeling sim. Label sim is global. That means this label that I created, sim, is global. That is what it means. String str means this str that is there is basically a string. Now word means what? I am storing n32 bit values in a successive memory words, w1, w2, like that. I am storing words here. Byte means what? I am storing 8-bit values here. Word means I am storing 18-bit values here. Dot space n means reserve n bytes to store variable. So space means what? We are reserving that much n bytes to store the variable. So dot space means I am reserving n bytes to store variable. Dot echo name comma constant means what? Define simple name with a value constant. That means I am going to define something that is a name, and that name's value that I'm going to define here. That is what echo means. Okay. Dot end means is the end of the assembly code. It is the end of the assembly code. So dot text contains the data section. Dot data contains the initialized data part. Global initialized part. Dot bss is the uninitialized. Dot section dot food contains a section with food. Align n is the b align n is the aligning n means 2 raised to n byte boundary. Aligning this data or instruction to a 2 raised to n byte boundary. B align n means align this data or instruction in a n byte boundary. Global sim means what? I am string global dot string str is the dot global sim means I am labeling sim to global. I am labeling this str to string. Dot word dot byte is this contains 32-bit values. Dot byte means 8-bit values it contains. Dot space n means that much space I am going to leave. Dot space n is the and dot align b align dot global dot string dot word dot byte. Dot byte means 8-bit values I am reserving. Dot space means what? You are going to reserve n bytes to the store variable. Fine. And dot echo name comma constant means I am defining simple name with value constant. So we are defining a symbol that is name and their value is here in the constant. Dot end means what? The end of the assembly code is dot end means. Dot space is important here and dot end is also important. Fine. So these are the important directories. Okay, so now here if you see, we can see some examples if you want. So we can see some examples now. So here if you see, first we have dot data. Okay, and this will dot data means what? I'm going to define something in A. I'm going to define this word dot word 10. Then dot text means what? We are going to start our global main. That means I'm going to write the global to be main. Main word contains the main instruction. Okay, in the next class we will discuss more about this. Fine.